A fireworks rocket. A fireworks rocket is fired vertically upward. At its maximum height of 80 meters, it explodes and breaks into two pieces, one with mass 1.4 kilograms and the other with mass 0.28 kilograms. In the explosion, 860 joules of chemical energy is converted to kinetic energy of the two fragments. Part A. What is the speed of each fragment just after the collision? Part B. It is observed that the two fragments hit the ground at the same time. What is the distance between the points on the ground where they land? Assume that the ground is level and air resistance can be ignored. Okay, so here is the fire rocket that is going vertically upward, and it explodes at a height of 80 meters into two fragments. So this is our x-axis, this is our y-axis. The mass of the first fragment, m1, is 1.40 kilograms. The mass of the second fragment, m2, is 0.28 kilograms. So there is chemical energy that has been converted into potential energy, kinetic energy of the system. So 1/2 m1 v1 square plus 1/2 m2 v2 square is 860 joules. So that's the chemical energy converted into kinetic energy. Now, at the maximum height, which is given as 80 meters in the problem statement, we must have the y component of the velocity to be 0 meters per second. It's not rising anymore. And the x component also is 0 because the rocket was fired vertically upward, because it was fired vertically upward. So it had an initial y component of its velocity, no x component, and there is no force on the x-axis. Therefore, its x component is always 0, but at the top of its maximum height, it's going to have y component 0 as well. So that's when it exploded. All right. So after the explosion, it's mentioned that the two masses, the two fragments, hit the ground at the same time. Okay, so what does this tell you? The distance traveled by the first fragment, delta x1, will be equal to v1 x component times t, and the distance traveled on the y-axis, delta y1, to hit the ground, will be equal to h max. And that will be due to its initial y component, v1y, t minus 1/2 gt square. The distance traveled on the x-axis for the second fragment will be its x component, velocity x component times t, and the distance traveled on the y-axis is h max, which is equal to v2y t minus 1/2 gt square. And we know that they're both hitting the ground. Delta y1 is equal to delta y2, and they hit the ground at the same time. So v1y and v2y should be the same. On the other hand, the net force acting on the system, net external force acting on the system, is 0, so we must have x component of the linear momentum conserved. So m1 v1x plus m2 v2x must be equal to 0. So m1 v1x must be equal to minus m2 v2x. m1 is 1.4, so 1.4 v1x must be equal to minus 0.28 v2x. So we find that v2x is equal to minus 5 v1x. It's in the opposite direction. Now, on the other hand, if I look at the external forces acting on the system on the y-axis, net external force acting on the system on the y-axis, this is approximately 0. Why? Because we have gravity, there is gravitational force. And why is this approximately 0? Well, if you compare this force to the internal forces in the system, it's negligibly small. So the forces exerted by the system particles on each other are so large. Well, we have a huge chemical energy that is turned into kinetic energy here, that the gravitational force becomes negligible and the system is approximately isolated. Okay, so that means we can write delta Py is approximately 0. So m1 v1y plus m2 v2y is 0. But also we had v1y must be equal to v2y. Therefore, what is the conclusion? These two are equal, and m1 v1 plus m2 m1v plus m2v equals to 0. This is only possible because the masses are not 0. v1y and v2y should both be 0 meters per second. So there is no y component of the velocities of these two fragments. Okay. Now, the change in kinetic energy is 1/2 m1 v1.4 v1x squared plus 1/2 m2 0.28 v2x squared, because the y components were 0. This adds up to 860 joules. So we find that 0.7 v1x squared plus 0.14 minus 5 v1x squared is equal to 860. So we obtain 4.2 v1x squared is equal to 860. So here I have substituted for v2x what I have found here due to conservation of linear momentum on the x-axis. And this gives me v1x is equal to 14.3 meters per second. v2x is equal to minus 5 v1x, which is minus 71.5 meters per second. And v1y and v2y I have found to be 0. Therefore, the speed v1 is 14.3 meters per second, and the speed v2 is 71.5 meters per second. So these are the speeds of the two fragments, and they're only on the they're moving on the x-axis. Okay, so part B asks me what is the distance between the 2 points on the ground where they land. Okay, so let's find out how long it takes to hit the ground. So h max is going to be equal to, because we have a zero initial y component, 1/2 gt squared. So this is 80 meters. Therefore, the time of flight will be equal to 160 divided by 9.8 square root. Then I can calculate the distance traveled on the x-axis. Delta x1 is vx1 times t. It was 14.3 multiplied with square root 160 over 9.8. So this gives us 57.8 meters. On the other hand, for delta x2, I have v2 times t, which is minus 71.5 square root 160 over 9.8, which is minus 289 meters. So I find that the distance between the two fragments, well, if we take this as magnitude, this is plus, but I have to note that they have opposite directions. So to calculate the distance between the two fragments on the ground will be 57.8 plus 289. One is moving in the opposite direction. So we find this distance to be 347 meters in total. Okay, so in this problem we have a fireworks rocket that was fired vertically upward, therefore it had no initial x component, and there is no force acting on the x-axis, so always the x component is 0, and at the maximum height the y component is 0. There is an explosion which converts the chemical energy to kinetic energy of the two fragments with masses m1 and m2. And after the explosion, it's observed that the two masses hit the ground at the same time. So using kinematics, I know that the distance traveled on the x-axis for m1 is v1xt, for m2 is v2xt, and this t is the same for both because they hit the ground at the same time. With an initial y component of their velocities, they would have v1 yt minus 1/2 gt squared as the displacement on the y-axis. Because I have written this as magnitude here, I should probably put an absolute value here, because this I have written it as an amplitude. Okay, so this will give me delta y1 equals delta y2, and the times are the same, implies that they have the same y component. At the same time, apart from the gravitational force, there is no external force acting on the system, and the force of explosion is so huge, we can approximately say that the linear momentum y components should be conserved as well, which gives us v1y and v2y should be equal to 0. So not only they're equal, but they add up to, well, they should be 0 because m1 plus m2 is not 0. On the other hand, the conservation of linear momentum on the x-axis gives us an equation between x components. v2x is equal to minus 5v1x. And we can use this information, the 860 joules of chemical energy converted to kinetic energy, 1/2 m1 v1 squared, which is v1x squared plus v1y squared, but y component is 0, so only v1x squared, and the same for v2. We obtain, when we substitute for v2x minus 5v1x that we found from conservation of linear momentum, v1 and v2. But we note that they have opposite signs, so that means the one fragment is going in one direction, the other one is going in the opposite direction on the x-axis. So we can calculate the time of flight because we have no initial y component of the velocity for these two fragments. 1/2 gt squared should be equal to at. So that gives us for delta x1, vx1 times time of flight, vx2 times time of flight for v2. And this is basically giving us a distance traveled on the x-axis, 57.8 meters for fragment 1, 289 meters for fragment 2, but because they're traveling in opposite directions, to find the distance between them, we need to add them up, and the final answer is 347